Hello, guys, and welcome to the part 2 of the Ethernaut Recap. So, in this concept, we were reviewing the key learnings of all the Ethernaut levels, and also we were going through the basic solution workflow. So, if you guys have not watched the previous video, I'll give you the link to it. So, without wasting any more time, let's just jump straight right into where we left off, which is Ethernaut level 18, magic number. From magic number, we got to know the low level building blocks of contracts such as the opcode and bytecode and how to create a contract using them. And we also learned the difference between the runtime code and the creation code. So coming to the actual problem itself, we need to create a contract such that whenever this function, what is the meaning of life is called, we need to return the right number. So the right number in this context is a trivial answer, which is 42, which is from the book The Hitchhiker's Guide to the Galaxy. So our goal is to return the number 42 when this function is called in our contract. So our constraint is that our contract should be only 10 opcodes at the most. So for this we need to learn what is opcode. So we need to create a contract using opcodes where our runtime code is less than 10 opcodes. So during this process we will learn all these things, and this took me a great amount of time because this concept was new for me. So let's get to the next level, which is alien codex. Alien codex is an extension of the underflow problem. So here also we'll be dealing with underflow and overflow, which was before the Solidity version 6.0. So the goal for us here is to become the owner of this contract, and this contract is using the ownable library. So we'll be learning how the ownable library stores the owner value. This is going to be the first slot of this contract. And if you could see here in the contract, there is no function to change the owner. So we'll be utilizing the storage slot of this array. We need to learn how array values are stored to avoid collision. So arrays use hash functions to determine the storage slots. So we'll be learning that. And here we have a function to reduce the length of the array. When the array is at length 0 and if we reduce this array without checking for underflow, the length of the array would become 2 to the power 256, which is the maximum number of slots available for the contract. By this step, we'll gain access to all the slots inside the contract, which means we'll also get access to the slot where the owner variable is stored. Our next step would be to identify the index of this particular array where this owner variable is stored. So for that we need to do a bit of mathematical relation to come up with the exact slot where it is stored. And we can easily use this revise function to input the index and the new owner variable we need to give here. Using this we can easily solve this particular level. Let's move on to the next one, denial. From the level name denial itself, we can identify that it is going to be a type of denial of service attack. So the key learning we have here is that whenever we are sending either to a contract, we should not send the entire gas to that contract because that contract can have malicious code in its receive or fallback function, which will drain all the gas we are sending, and it will render the remainder part of a code unusable. And as a side note, we'll also be learning the difference in the methods that we use to send ether, such as send, call, and transfer. So coming to the actual problem, we have two parties involved here. One is the partner and the other one is the owner, and we can become the partner. Here is this withdraw function which anyone can call, which would send 1% of the balance of this contract to the partner and another 1% to the owner. The problem here is that the partner is called first and we are using the call method by not specifying the gas, which means the entire gas of this transaction is going to be going to this partner contract via this call method. There, this partner can be a contract which has an indefinite loop which will drain entire gas of this transaction. By doing so, there will be no gas left to send the owner using this transfer function. So the owner will never receive this amount. So we are denying service to the owner by not transferring him this. So this is how we solve this, and let's move on to the next level, which is going to be shop. Shop is quite similar to the previous level which we have finished, which is the elevator. From the elevator, we learned that whenever we are using an interface, we should be very careful because they can use the state variables present in their contract. So to avoid that, we use this restriction modifier of view or pure. Here we have employed our learnings and we have used the view modifier, but there is also another small loophole which we will find out. So here the problem is that here is this shop contract and there is a product which has a price. Our goal is to buy this product for a price less than the quoted price of 100. So our goal is to set is sold to true and the price should be lesser than that of 100. And the only way to do that is through this modifier, sorry, not a modifier, but this require statement, which requires that the price of the buyer should be higher to enter this modifier. So if it were for a non-view function, we would have access to the state variables and modify them. Due to that, for the first time this buyer.price is called, we would give a higher value, and using the counter for the second time it is called, we will give a lower value. But we do not have access to change the state variables because we have the restriction of view. But there is this loophole of using the state variable of the contract itself. If you look here, the is sold variable is set to true after it is called for the first time. So we can simply view the state of this shop contract to change our values. So for the first time, the price is called is sold is going to be false, and whenever it is false in our contract, we are going to set the value to be higher than 100. And for the next time, is sold is going to be true, and if is sold is going to be true, we are going to set a lower price. So this way, the first time it's going to be more than 100, and for the second time, we can set the price to lesser than 100 and solve this challenge. Let's move on to the next level, DEX, decentralized exchange. Like in the level where we got an introduction to how an ERC20 token works, in this challenge we are getting an introduction to how a decentralized exchange works. This contract has all the basic building blocks of a decentralized exchange, such as the add liquidity function, the swap function, and here we have a formula to get the swap price. So basically, to obtain the output amount, we multiply the input amount into the two token divided by the from token balance. This is based on the balance of this particular contract. And coming to the actual challenge, we have these two tokens, token 1 and token 2, and our goal here is to drain at least one of these token. So here we need to bring the balance of either token 1 or token 2 to 0. The way we do that is by utilizing this swap function and a small loophole we found in this formula. Here this formula works based on the basic supply and demand, where whenever the amount of or the liquidity of a token is less in this contract, the value of that particular token is going to be high. Utilizing this, we can easily swap these tokens multiple times to get a higher number of token, to the point where for a particular token we have a higher balance than the contract itself. Then we can easily swap one token to another and bring the value of one token to 0. The key learning here is that we should not be determining the swap prices based on just a single point. Here the swap price is determined based on the balance of this contract, and it is just a single point, and due to this the price can easily be manipulated. In the real world, this particular token is not going to exist just in this only one DEX, but it would be available at a different exchanges, and a lot of exchanges is going to have these tokens. So we need to get them into consideration also to determine the accurate prices. The way we obtain them is through oracles such as the Chainlink Oracle, which will reliably give us information about the prices of tokens, which is decentralized. And another key learning here is that the DEX should have sufficient balances, because if a DEX has low liquidity, the price can easily be manipulated. So just because in this contract the liquidity was only 100 and 100 for both the tokens, it was a very less amount and the user could easily manipulate it. And once he got a higher balance, then he could easily crash down the balance of the token one. And I also forgot to tell you about another key factor, which is the floating point error in Solidity. So Solidity does not have support for floating points or decimal points. So whenever we divide the value, we would get a decimal value, but Solidity rounds it off to the nearest whole number. So in this mechanism, we can easily arrive at 0, as it is going to round it off. And I think that will be it for this particular level. Let's move on to the next level, X2. X2 is basically the same contract as the previous level, with one key change which lies in this swap function. Earlier we had require statements which restricted us to swap only between this token 1 and token 2, but now there is no such require statement to restrict this from and to address. So basically, which means that we can swap between any tokens, and let's say we can introduce our own token and we can swap between this token 1 or token 2, and the value of our token will also be determined by this same function get swap amount, using the same formula of utilizing the balance of this particular contract. And coming to the goal of this level, the starting dynamics are the same, where we have 10 tokens of each, but the end goal is quite different, where we have to drain all the balances of both the tokens. For the previous level, we would have drained only the one token, but for this level, we would be draining both these tokens. So the solving notion is quite simple. What we do is we are going to be swapping between our own token and either of these one token. First, we will do a bit of math like the previous level to determine how much token we need, and then we are going to send that particular amount of token to this contract to get the balance of this contract to have that token. And then we would initiate the swap from token 3 to token 1. So we would send the token 3 to this contract and we would obtain the token 1, and then we repeat the process and drain token 2 also to beat this level. So the key learning here in this level is that whenever a decentralized exchange is going to allow swap between any two tokens, its value should come not from just a single place. So let me rephrase it. So whenever a decentralized exchange allows any token to be swapped, the value should not come from just a single place. For example, this same scenario can occur in the real world, where a user brings in a worthless token and uses it to swap a valuable token 1 and token 2. So here the value for that token 3, the user added token, comes only from this equation, which relies only on a single source, which is the balance of this contract. So using this, a malicious user can bring in a worthless token and sweep all the valuable tokens and leave the contract with the worthless token. Let's move on to the next level, Puzzle Wallet. Puzzle Wallet is another proxy pattern contract which we need to hack. And for this one, I'm not going to explain every bit of the code, but only going to focus on the main part and skipping the few minor steps that we need to take. So coming to the actual goal of the contract, we need to become the admin, and this is going to be the storage contract. We need to become the admin here, and this is the logic contract. And if we can see, this storage slot coincide with this max balance. So to become the admin, we should change the max balance, and to change the max balance, we have this function which requires the balance of this contract to be 0, which is currently not. So this contract will have already around 0.01 ether, and our goal now is to drain that to 0 to change the max balance. And if you can see here, we will have this execute function. It is kind of like a withdraw function where user can withdraw money that they have already deposited using this deposit function. So we have an issue here that to withdraw a balance, you should have already deposited it. So even if I deposit 1 ether, I can take out only 1 ether, but that pre-existing 0.01 ether in the contract will remain. So that is where this multi-call function comes in. This function is the main function of this contract, and to solve this contract we need to understand what multi-call is and how it works and why we use it. Multi-call, as its name suggests, is a way to call multiple functions in a same transaction call. So it basically utilizes a delegate call on this contract itself. It's going to delegate the call to the same address of this. So the main goal of using a multi-call is that this multi-call input is going to have a bytes array where each element is going to be a function call. So for example, let's guess that this multi-call input is going to have 5 values, and 5 is going to be five function calls of this contract. So basically what we did is that in a single transaction we call 5 functions, but we paid only the gas for a single transaction. So this way we can reduce the gas for calling multiple functions. So here our key learning here is going to be that the value of message.sender and message.value is going to be preserved through the chain of delegate calls. So what I mean here is whenever delegate call is performed on a function on this contract, the value of message.value and sender is going to be the same. So we can utilize this one small logic here. The way how we utilize is that in this multi-call, for the first input we'd be directly calling this deposit function, and the message.value we'd be sending for this multi-call function is going to be 0.01 ether. So our balance will now be 0.01 ether and the contract balance will be 0.02 ether. And that finishes the first element of this array. And the next element of the array, what we're going to do is we're going to call multi-call itself, and for the data we'll be calling deposit. So for the second function call, this is going to call multi-call, and we'll be given our value as 0.01 ether, but the message.value is going to be the previous 0.01 ether. So this way, using only one 0.01 ether, we have increased our value 2 times, which is going to be finally 0.02 ether, but the balance of the contract is just going to be 0.02 ether. So this way we can easily execute and drain the funds and become the admin of this contract. So let's move on to the next level, motorbike. Motorbike is also another upgradable contract, but this one is quite simple. It uses EIP 1967, and this particular level was easy for me to solve because I had already known this particular protocol and how it works, so that I could easily come up with a solution. So coming to the goal of this contract, it is mentioned here that we should self-destruct the engine of the bike. This indicates that in this engine, here we have a function upgrade to and call, which will set a new implementation and call it. So we need to create a contract which will have a self-destruct function. We need to upgrade to it and call that particular self-destruct function. To upgrade to and call, we need to first go through this authorize upgrade function. This function requires that the message.sender needs to be the upgrader, and if we look through the contract, the only place we can become the upgrader is through this initialize function. This initialize function uses this initializer, which is inherited. The initializer makes sure that this function is run only once when this is created. So this function has already run once when it is has been called by this motorbike function. But the loophole here is that it is only from the context of this proxy contract, but not from the context of this contract itself. So to utilize this loophole, first we need to identify the address of this particular engine contract. We can obtain the address through this implementation slot. So by getting the value from this implementation slot, we can get the address of this engine, and from there we can directly call initialize, which has not been called yet, and we can easily become the upgrader. The key learning here is that whenever in a proxy contract we are using this initialize function, we should be making sure that this function is secured from both the routes. So both from the context of the proxy contract and directly itself, we should secure both the routes to make sure that no one utilizes this initialize function for malicious activity. So let's move on to the next level, double entry point. The double entry point level is a collaboration between FOTA and OpenZipline. Here they want us to find the issue and create a FOTA detection bot such that it detects and prevents the vulnerability. So for the scope of this particular video, I am not going to go into the process of creating a detection bot, but I am going to just focus on the particular issue, which brings us to this double entry point contract. This is a token contract, an ERC20 contract. So as the name implies, double entry point means that this contract is going to have two entry point. One is through the traditional route of the transfer function. The second one is going to be a delegate transfer, such that another contract is going to delegate the transfer to this contract and the tokens is going to be transferred from this contract. And using a modifier like this only delegate from modifier, we can restrict to get delegations from one particular contract, such as this legacy token contract here. And another part of this level is this crypto wallet. This has a sweep function. This function is used in the real world also. This function sends any remaining fragments of the of a token to the owner. So there might be instances where there are small amounts of token left over. So we transfer those leftover tokens to the owner, except the underlying token. The underlying token in these types of contract will be the token which is the basis of the logic of the contract. And if we swap or sweep these particular tokens, the logic of the contract is going to get broke. So we should prevent the transfer of this underlying token and we should not sweep it. But as you can see here, the exploit is very straightforward. We can sweep the legacy token, and this legacy token has this delegate function. So whenever we are going to call the transfer, it is going to delegate to this double entry point token, which in this context is going to be the underlying token. So just by simply calling the sweep function with the legacy token, we are going to sweep the and make the crypto wallet go broke. So the key learning here is that whenever we are using a double entry point token, we should be aware of the edge cases and we should experiment to find out what are all the edge cases. And also with a crypto wallet where we are using a sweep function, we should make sure if the underlying token has another entry point where a malicious user can take advantage of it. So let's get going on to the next level, which is Good Samaritan. The Good Samaritan level introduces us to the concept of custom errors and how they can be used against us. Here at this level, we have this Good Samaritan who is going to give us money whenever we request for it. So they're going to give us 10 tokens. Our goal here is that we should drain the entire balance of this contract. And to do that, we have this transfer reminder function. This function is to be only called when we encounter the error not enough balance. If we look through this coin contract, which actually houses the tokens which are going to be sent, this insufficient balance is the error is sent only when the actual balance is insufficient. But here, if we look at this transfer function, we can see that we are calling the notify function in the particular caller contract. So what we can do is we can create a contract such that it adheres to this iNotifiable interface and has this notify function which will throw the error of not enough balance. So this way we will obtain this not enough balance and we will send the entire reminder to the caller. So the way this works is our key learning. Our key learning here is that the custom error can be thrown by any contract down the line and it will be interpreted the same as if it were thrown by the contract itself. Meaning that if we are doing any external calls to any contract, if that contract sends the custom error we are expecting for, that will be treated the same as if it were given by the contract itself. So the key learning here is that whenever we are making a state change or anything important using a custom error, we should make sure that there are no external calls to other contracts where they can throw this error. Let's move on to the next level, going to be keeper 3. So we have reached the last two levels of Ethernaut, and for these two levels I'm not going to give you a good overview because I have already made a full length video for both these levels, Gatekeeper 3 and the switch level. So I'm going to give you guys the link down below so you can go and view the full length video. For now I'm going to give a very quick overview of both these levels. So the Gatekeeper 3 is similar to all the both Gatekeeper levels where we have 3 modifiers and we need to get through them. So for this particular level there is no basic fresh concepts we are going to learn, but we are going to employ the previous concept that we have learned. And let's move on to the next level and the final level of Ethernaut switch. And for this level also I have created a full length video which is more than half an hour long. So the content is more than 30 minutes and you can learn many things from there. So the main learning of switch is how to manipulate the call data, and I have started from the fundamentals of call data structure and gone all the way to solving this particular level. So please go through that particular full length video to know about solving this switch level. So this is going to be it for this particular video and I am hoping to see you guys soon on the next video. Bye.